The next topic that we talk about in kinetics is a second way to calculate the rate of reaction, and it is using a type of equation called a rate law. Before we get into the definition of it, it's helpful to review the types of rates that we can refer to. What we were just discussing with rate expressions were average rates, rates over a given time period. We could also have an instantaneous rate at one specific time in over the course of a reaction. For rate laws, we specifically use an instantaneous rate at time zero, and that is called the initial rate. All of these rates will have different values, and so it is helpful to report how we're calculating rates so that we know what to expect and how those might change. Again, before we get into specifics, we're back to our graph for the decomposition of hydrogen peroxide. So again, an average rate would be looking at any two measured points in here and calculating the change in concentration over change in time over an average. An instantaneous rate would be looking at the slope of the tangent at some specific time. So if I could measure and calculate the slope of this tangent, that would give me an instantaneous rate. And I'll add it in here. This first one that I referred to is our average rate. What we're going to be talking about for rate laws is called initial rates. So it's the same as instantaneous, but it's specifically at time zero. And so if I can take the slope of this tangent, this is measuring what's called our initial rate. The format that we use for rate laws, it is still a way to calculate the reaction rate. But again, because we're measuring it at a different point and under different circumstances, we use a different equation for it. If I have a sample equation, A plus B converted into C plus D, my lowercase letters are my coefficients in here. The format for a rate law is we're calculating the rate, and again, this is specifically of a given reaction. Our little k in here is called a rate constant. This does have units, and as we get into calculations, we'll talk about how we determine what those units are. The brackets, square brackets of A and B, are specifically talking about concentrations, and we only use reactant concentrations. And again, that's because we're talking about initial rates. At time zero, we don't have any products yet, and so we don't use products in our equations for rate laws. The key thing in our rate laws are the values of X and Y. Notice these exponents up here. These are called the orders of reactants. And notice that I used X and Y. I did not use A, B, C, or D. These are not necessarily the same as the coefficients. It's possible for the order to match the coefficient, but we can't just use the coefficient to tell us the order of a substance. And so this is our general format for a rate law. A couple of examples to show you the difference between coefficients and orders. Down here we have the reaction between bromine and formic acid. This is formic acid. Again, I'm only interested in looking at the reactants. I don't need to look at the products here. The experimental rate law was determined to be, again, we start with our rate constant. Bromine is first order and formic acid is zero order. Now remember, we're describing exponents here. Also remember that anything raised to the zero power becomes just a 1. And so this rate law could also be written just like this, where the rate equals my rate constant times the concentration of bromine. Recognize that a 1 here is optional. It does not need to be included. All right, it is implied to be a 1. And again, I could completely leave formic acid out of this because raising it to the zero power makes it just the value of 1. Some other examples of equations and their experimentally determined rate law are listed here. Notice that coefficients don't always match the orders. Sometimes they do. So here, notice that iodide does match its coefficient coincidentally. Same for hydrogen and iodine down here. Since we can't use coefficients, we do have to use experimental data in a table that looks like this. So notice for my concentrations, I'm only listing my reactant concentrations, and then we're given values for the initial rate. We carry out multiple trials here with the idea that if I want to solve for the order of bromide, when I'm describing the order, I'm describing how does a change in its concentration affect the rate of reaction. So we need to find two trials where only one reactant is changing, the one that we're examining, and the other two are held constant. Then we can compare the change in rates to the change in concentrations to determine the order. And just so you know, for purposes of this class, your values for orders will only be 0, 1, or 2. They can be anything. They can be negatives, they can be fractions, they can be larger. For purposes of this class, we will only use these three values. So notice in this slide, we have the same table here. When I want to solve for the order of bromide, I'm going to use trials 1 and 3. Because notice that bromide's concentration is changing, but bromate is constant and hydrogen is constant. So again, I want both of these other reactants to be held constant so I can see how the change in concentration of bromide affects the rate of that reaction. On my next few slides, I'm going to go through the setups to solve for this. To solve for the order of bromide, what we're going to do is set up a ratio of our two rate laws. So again, we decided that we are going to use trials 1 and 3. And so what I'm going to do is set my rate law up as a ratio. I'm setting up all my information from trial 3 on top because that will give me larger numbers. So when I go to reduce everything down, I get a whole number. If you flip it and put 1 on the top, the math still works out. You're just working with fractions instead of whole numbers. All right, so referring to our table of data. So again, remember our rate law is rate equals K. For this reaction, we have bromide as X, bromate as Y, and hydrogen as Z. X, Y, and Z are completely arbitrary. They're just my favorite variables. So anything other than your coefficients can go in here. Now, before I plug in numbers, realize that we specifically chose trials such that the bromate concentration would be held constant and the hydrogen ion would be held constant. Since those concentrations are constant, those cancel out. So when I go to plug in values, I'm only going to plug in my values for the rate and my bromide concentration. Notice also that my rate constant is going to be constant, and so it will also cancel out. So when I plug in these values, again, I'm picking everything from trial 3 on top. So here's my rate value and my concentration value. And on the bottom, we have everything from trial 1. So we have our equation. Now we can start simplifying. Realize that our rates here will reduce down to just a 3. And again, the reason I like my bigger number on top is so that I end with a whole number down here. And now remember our rules of exponents. So here, my two values of concentration are raised to the same exponent, so I can reduce the ratio of these two numbers and still raise that to an x. Now let's pretend we don't know what the value of x is going to be. Hopefully we can see that, but let's pretend. If we're ever working with data from lab, we get numbers that aren't going to be nice round whole numbers. To solve for an unknown exponent, we use the function of log base 10. We take the log of both sides. That has the effect of moving our x down in front. And so then to get x by itself, we divide both sides by the log of 3. And so now we can quickly see that our value of x, our order of bromide, is a 1. All right, let's go back to our table and find 2 trials to solve for bromate. So again, we want to pick 2 trials where this is the only one changing, where the other reactants are held constant. Hopefully you see that trials 1 and 2 will work for this. So for bromate, we're going to use 1 and 2. And again, I'm going to set up to have my larger number on top. So my rate for 2. Not going to write the whole equation this time. We know the setup for it. So there's our rate values. We know K is going to cancel. And really, we just need to know our value for bromate, because we deliberately picked values that would cancel for our other reactants. When we simplify everything down, we get this equation. And again, if you don't see it right away, when you use your rule of logs, you will determine that y equals a value of 2. And then one last pass, we need to find 2 trials where hydrogen is changing and the other 2 are not. Notice for this one, that's going to give us trials 2 and 4. Bromide is constant, bromate is constant, only hydrogen is changing. And so for hydrogen, we're going to use 2 and 4. And again, plugging in our concentration. Remember, we assigned hydrogen to be Z. Whatever variable you wanted to use for that order is totally fine. Notice our rate comes out to a ratio of 1. But our concentration is a ratio of 2. And so again, think about what does the value of Z have to be as an exponent so that we end with a value of 1 overall. Again, if you can't see it right away, feel free to use your rules of logs, but realize here that hydrogen has to be an order of 0. So let's think about what that means. Let's talk about what the orders mean. Realize here that we doubled our concentration of hydrogen, right? Between trials 2 and 4, our concentration doubled, went from 0.15 to 0.3. But our rate stayed the same. It was constant, no change, stayed the same, however you want to phrase it, which means that the change in concentration of hydrogen literally has no effect on the rate of our reaction. And so therefore, this triangle of dots is a therefore. Therefore, hydrogen is 0 order. If we go back to bromide and take a look at this, again, discussing the shortcut version to figure out our order, notice that bromide, as we went from trial 1 to trial 3, bromide tripled in concentration, right, a 0.1 to a 0.3. The value of our rate also tripled, right, a 1.2 up to a 3.6. When you have the same amount of change in both concentration and rate, this is always going to be a first order reactant. So if they both double, if they both triple, if they're both cut in half, if they both quadruple, that is always going to be first order. So the same amount of change is first order. So 2 ways to figure out if something's going to be second order. First of all, process of elimination. If it's not zero order where the rate's constant, or if it's not first order where we have the same rate of change in both concentration and rate, then it has to be second order. Or we can simply simplify down our concentration and rate information and solve for the order for this one. But notice that again, exponents, or the orders are exponents. And so what I'm doing is I'm squaring the amount of change. So if, for example, I had a reaction, let's say my concentration tripled. If this is a second order reactant, what is the amount of change for my rate? Again, remember our orders are exponents. So if I have a second order reactant, the rate of change for my rate would actually be a ratio of 9. Right? So again, orders are exponents here. So the last few slides I want to leave you with in this section. One is the shortcut for determining orders. So I've already mentioned this as I went through the slides. It's just here in word form for you to read through. And then also describing what the orders mean. We've already discussed this as well. So just more for you to read through to better understand the orders of reactants.